Today's topic is differential equations reducible to exact form, in which initially the given equations are not in the form of exact form, but we can reduce these equations into exact forms by considering suitable integrating function. So integrating functions are basically such expressions through which the given non-exact differential equation, the given non-exact differential equations can be converted into exact differential equation. So if we find an integrating factor for this non-exact differential equation, then after multiplying this non-exact differential equation with that integrating factor, and the reduced form will be in the form of an exact differential equation, and we can write the solution of the exact differential equation. Then using that result we can easily write the general solution of given differential equation. So in this topic reducible to exact form, we have to obtain the integrating factor for the given differential equation when it is not in the form of an exact form. Suppose we have given the first order and first degree differential equation, which is in the form of m dx plus n dy is equal to 0, and initially which is not in the form of exact form, means del m over del y is not satisfied, is not equal to del n over del x, which means that the necessary and sufficient condition for the exactness is not satisfied here. So using the exact form, we are not in the position to write its general solution at this situation. So we have to reduce the non-exact form into exact form. Today we will cover these two methods, method 1 and method 2. Suppose if we find this expression, that is del m over del y minus del n over del x, and divide this difference with the function n. Suppose the result is obtained as the function of x alone. Suppose this function is taken as fx. Then for such situation, the integrating factor is taken in the form of e raised to the power integration of that particular function, and after multiplying the given equation using this expression, the resulting form is by default will an exact form, so we can write it's a solution. And the second rule is we have to find this difference, that is del n over del x minus del m over del y, and suppose if we divide this expression with m, and the resulting value or the resulting expression is obtained as the function of y alone. Suppose this function is treated as f of y, then for this situation the integrating factor is taken in the form of e raised to the power integration of this function with respect to y. It means when we multiply the given differential equation, which is non-exact differential equation, using this integrating factor, the resulting differential equation is in the form of exact form, so we can write it's a general solution. Let us consider examples for these two methods. First example, suppose we have to solve this differential equation, which is 2y dx plus 2x log x minus xy dy, and comparing with the standard form, which is m dx plus n dy is equal to 0. First we have to verify that whether the given equation is exact or not. If it is exact, then we can write it directly its general solution. If it is not exact, then we have to obtain suitable integrating factor. Suppose here, comparing with this form, we have m is equal to 2y and n is equal to 2x log x minus xy, and To verify the condition of exactness, we have to obtain the partial derivative of m with respect to y, which is 2, and the partial differentiation of n with respect to x, which is obtained as this one. Here, the value of del m over del y is not equal to the value of del n over del x, which means that given equation is not an exact differential equation. Initially, this equation is not an exact differential equation. So we have to obtain the integrating factor. If we apply the first rule, we first evaluate the difference of del m over del y minus del n over del x. This 2 will cancel out. So the result in minus 2 log x plus xy. Suppose if we divide this expression with the function n, which is 2x log x minus xy, this term will cancel out, so we obtain minus 1 over x, which is purely a function of x, which means that this rule, that is method 1, is applicable, that the value of this expression is obtained as the function of x only. So this function is treated as f of x, and then for this situation the integrating factor for the given differential equation is taken to be e raised to the power integration of this function, e raised to the power integration of minus 1 over x, and the integration of minus 1 over x is e raised to the power minus log of x, and using the property of logarithmic and exponential function, the value of this expression is 1 over x. So 1 over x behaves as an integrating factor for this differential equation, which means that if we multiply this differential equation, which is initially in non-exact form, if we multiply the given differential equation with this integrating factor, that is 1 over x, the resulting equation is 2y by x dx plus 2 log x minus y dy is equal to 0, which will be surely in the form of an exact differential equation, and this can be verified by again comparing this form with the standard form, which is m dx plus n dy is equal to 0. Here the m function is 2y by x and n function is 2 log x minus y. Suppose if we compute the partial differentiation of this m function with respect to y, the answer is 2 by x, and the partial differentiation of this function n with respect to x, the answer is 2 by x. Here both the partial derivatives are same, which means this form is an exact form, so we can write its general solution, and the general solution is simply we have to integrate this m function with respect to x taking y as constant, and we have to integrate only those terms of n which do not have x. So integration of minus y dy is equal to c. Integration of 1 over x is log of x. Integration of minus y is minus y square by 2 is equal to c, which is the required general solution of given differential equation. Now considering another example. This example is actually based upon the method 2. Here again we have to solve this differential equation, which is in the form of m dx plus n dy is equal to 0. Comparing with the standard form, we obtained this m function and n function, and to verify that whether it is exact or not, we have to compute the partial differentiation del m over del y and del n over del x. Here we can observe that both the partial derivatives are unequal, which means that given equation is not an exact differential equation. Thus we have to evaluate the suitable integrating factor. Suppose if we differentiate these two partial derivative del n over del x minus del m over del y and divide it with m function, so we obtained as the function of minus 3 over y, that is purely a function of y. If this situation is satisfied, then we can write the integrating factor for given differential equation, and the integrating factor in this case is simply e raised to the power integration of this function. Therefore integrating factor is e raised to the power integration of minus 3 over y, which is integration of e raised to the power minus 1 over y is log of y. Then using the property of logarithmic function and exponential function, the integrating factor is 1 over y cube. What does it mean? It means that if we multiply this non-exact form with this function, so the resulting form is obtained in the form of an exact differential equation. So we have simply multiplied the given equation with this integrating factor. This form is obtained. Here, to verify that whether it is exact or not, we have to compare this form with the standard form. M dx plus n dy is equal to 0, and we have to find del m over del y and del n over del x. Del m over del y is obtained as 1 minus 4 over y, and del n over del x 1 minus 4 over y. Since both the partial derivatives are same, which means that given equation is an exact differential equation. Therefore its general solution can be written as simply differentiate this m function with respect to x, taking y as constant, and differentiate only those terms of this function which do not have x. So 2y is the only term, is equal to c. Simply integrate this with respect to x, taking y as constant, so this whole term is treated as constant. So the integration is simply x, plus integration of y is y square by 2. 2 will be cancelled out. So this is our required general solution. Thank you so much.